When attempting to explain how an object is moving in free space, it may be convenient to draw a motion diagram. These diagrams are generally used for illustrating the translational characteristics of an object in only one dimension, so the object of interest will often be confined to traveling in only one direction. But there are still numerous applications for a motion diagram, and even complex movement profiles can often be adequately described by a combination of motion diagrams. For this example, consider the motion of this toy car. After winding up the internal spring mechanism, the car is released from rest, at which point it begins to accelerate. To construct a motion diagram, we will need to know the velocity of the car at various points in its journey. Let us say that 1 second after release, the car is going 2 meters per second. Then 2 seconds after release, it is going 3 meters per second. And 3 seconds after release, it is going 4 meters per second. To construct our motion diagram, we will begin by placing a dot that represents a particle form of our toy car. Above the dot, we will write a time index so that anyone else reading our diagram will know what time in the car's journey this dot represents. Since this is our first dot, it will represent the first data point collected for the car, which was the 1 second after the car was released, thus t equals 1 second. Next, we will add to the dot a vector representing the velocity of the car. Assuming that the positive direction is to the right of the page, our velocity vector should point to the right as well. And the magnitude of this velocity vector should represent the velocity of the car at this instant. It may be a good idea to develop some form of scale when drawing these diagrams. This can be accomplished by using graph paper or by using the markings on a ruler. For this example, 1 centimeter on the paper will represent 1 meter per second. This means that our first velocity vector should be 2 centimeters long to represent the car's velocity of 2 meters per second. Using this same process, we will then add more dots and velocity vectors in sequence to represent the data points we collected for the motion of the car. Notice that the dots get progressively farther apart. This is because the car was accelerating. And simply by looking at the diagram, we can also determine the direction that the car was accelerating. This finished diagram now graphically depicts the motion of the car after it was released from rest. If instead the car was cruising on the highway at a constant velocity, would we expect the motion diagram to look any different? Of course it would, since a particle moving at a constant velocity would be represented by equally spaced dots with identical velocity vectors. The diagram for the car traveling at a constant velocity would have completely different characteristics from the diagram of the car undergoing an acceleration. Now that you have a better understanding of motion diagrams, you should be able to apply this powerful tool to future laboratory experiments.